Okay, so today we are going to learn a little bit more about interfacing, or maybe initially about how to interface a microprocessor to the real world. So the microprocessor, let's say Atmel 328P, speaks to the world or communicates to the world via the different pins that it has. Now, as if we have a look at the data sheet of the 328P, we know that it has three sets of uh, pins on B, C, and D. I mean, they're grouped 8 pins on B, 8 on C, 8 on D, and besides that, it has VCC ground, reset, and a couple of other pins. So, what are these pins and how do they actually work inside the hardware? This is what we are going to try and understand now. So, you can have a look at all the registers which are applicable to the processor. In this case, 328P, by clicking at I/O here. You click at I/O, you will get the screen with which you can actually visualize all the registers in real time. So, so what I'm going to do is I'm going to write a small program to set port B, all the pins on port B0 to port B7 as output. So if we click on port B here, then we can see that there is a DDRB. That means um, data direction register. So if it is set as logic 1, then it will give out data. And if it is cleared, which means there's nothing on this, then it works as these pins work as input pins. So let's just make all these pins in one go as output pins. So remember, they are declared as output pins, but they are not outputting at the moment. Okay? So the simple instruction for that is DDRB is equal to 01FF. So uh, what does this mean? This actually means, let's first compile this. It's compiled and it's now stepping through. And we go to the next stage. At this moment, nothing has happened. And the moment we move forward, you see all these pins have turned red. Red means basically they have changed state, and in the next step they will remain red. Would turn blue. So essentially, all these pins have become output pins. So let's just go back, and now let's say I would like to now zero this XFF is actually translated 255. Let's just do this once more. And once we've done this, it becomes X 0xFF. So rather than declaring this in a hexagonal, I try to do this a bit differently. 1111111. So 8 ones over here as a binary number. So let's just file this and then run this. So as you can see, all these registers are now 1, which means all these pins have been declared as output pins. Now let's go back. For example, you only want to declare this pin 0, PB0, this is PB0, this is PB1. You only want to declare PB0 as a output pin. All other pins should remain. So 3, 4. So this is what we do. We declare these 7 pins as 0 and the last one as 1. So let's just compile and then step through. Everything is clear at the moment. Voila. So this is how we can declare do a pin setup very quickly inside and actually visualize using the powerful Atmel Studio how this actually works. So let's take this a step further. Now we have declared in this instruction this pin B port DDRB uh, this be an output register output pin, let's say. But now we want to actually um, give voltage to this pin so that it can say let's say light up an LED. How do we do that? So if we have a one here, logic one here, it means that it has a voltage. It is connected to VCC, and if it has voltage here, then it can actually light up an LED. So let's say, let's just go back to our, or let's just keep it like this. So let's say port B is equal to, let's copy this here. Now let's see what happens. Compile, and then we step through. So we have one here, and then another one here. So if this is declared as an output pin, and at the same time this is declared as a, this gets a voltage on it, then you have an LED which can light up. So it's a very simple application, but by the power of this software, you can actually visualize how this change in state inside um, the microcontroller is actually happening. So that's it for today. In the next parts, we will see more about the power of these pins. Thank you.